over to you. Okay, so we
right.
should be alive now. Sorry, sorry for the delay, everyone. We've been having some back-end tech issues. It's been solved now. Just because I know some people are also on YouTube right now. I could see the analytics. Okay. Yeah. So I was just hearing myself because I was in the on YouTube. Sorry for that. If you can just confirm whether you can hear us and see the screen share from Adrian. So you should be seeing category theory stuff on the screen. Just confirm with yes or no. And then I will hand over to Adrian. I think there is a bit of latency as well. And I think some people are probably just on listen mode with the note. Can anyone confirm whether you can see? Yes, okay. Thank you, Tony. Okay, so yeah, so without any further ado, I will hand over to Adrian. Adrian, the floor is yours, and thank you so much again for taking your time for doing this.
All right, great. So for those who weren't here last time, I'm Adrian, and this is an Ask Me Anything session on category theory. And basically, I will just be telling you about categories in a somewhat systematic way. And when I get questions from you, I will answer them. And ideally, I'll spend most of my time asking questions. But if I don't get any questions, I'll just slog on with the exposition on category theory. So this is the second installment of this Ask Me Anything, and the last time was 3 weeks ago. And 3 weeks ago, I mostly just focus on giving a definition of what a category is, and I gave some examples. I told you guys what a functor is, and I also finished by telling you what a natural transformation is. So I'll first just go over what we did last time, and then I'll start going through a bunch of examples of various categories, and then I will start telling you about universal properties and the sort of things one can do inside of a category. All right, so last time I started off by saying that informally, if you have some sort of objects of the same type, like for example, sets, vector spaces, groups, topological spaces, and so on, and you have some notion of morphism between these types, then in this case, you probably have a category. And then I gave you the definition of a category, and that's this whole mess here. So let's just very quickly go through the most important points here. Right, so a category has 4 pieces of structure. So the first piece is you have some collection of objects. So for example, these would be the collection of sets, or the collection of vector spaces, the collection of groups, the collection of topological spaces. And then for any 2 objects, you have, so here for any 2 objects, you have a set of morphisms from the first object to the second object. So in the example of sets, these are just maps of sets. In the example of vector spaces, these are linear maps. In the sets of groups, these are group morphisms. And in the example of topological spaces, these are continuous maps. So these were 2 pieces of structure. And the third piece of structure, whenever you have 3 object, you're given a way of composing morphisms, right? So you look at morphisms from X to Y, and look at morphisms from Y to Z, and if you take a look, you see that the letter Y appears twice, right? So we're looking at morphisms which start at X and end at Y, and morphisms which start at Y and end at X. And then as a piece of structure, you have some sort of composition. So you take pairs of morphisms, FG, and you send them to the composition, F and G. And then the last piece of structure was that for every object in C, you have the identity morphism, and the identity morphism does exactly what you think it does. When you pre-compose with or post-compose with the identity morphism, you just get back the morphism you started with. So that's this axiom down here. So now I'm giving you them out of order. The first axiom is that if you have a triple of composable morphisms, it doesn't matter in which order you compose them. Then I was asked about some references, and 3 references that I really liked are Leinster's basic category theory by Arady, and categories in context by Real. I also got an email asking about the book. Let's have a look. Right, asking about the book by Eugenia Cheng, The Joy of Abstraction. Unfortunately, if the person who wrote this email is watching, I've never looked at the book, so I don't know. I can't say if I think it's any good or not. And then I spoke about how there are basically 2 levels at which one can do category theory. One is in terms of an organizational principle. So basically, whenever you have a bunch of objects and morphisms, then you know that you have a category, and then you can talk about these objects and morphisms in the same way across vast domains of mathematics. And in the first instance, it's just a case of whenever you encounter the same structure over and over again, it's a good idea to give it a name, just so you don't have to mention you don't have to start from scratch every time and tell everyone, oh, I have a bunch of objects and I have a bunch of morphisms, and here's a way to compose them, and here are a bunch of rules. You can just say, I have a category with these objects and these morphisms, and then your interlocutor will know what to do. And I gave 2 very peculiar examples of categories. The first peculiar example was that of a monoid. So the monoid is the structure where you have a set together with some notion of composition and an identity morphism. And every single monoid can be viewed as a category with only one object. So, and if you have a monoid M, the category which associate to it, I call it BM. And then I quickly discussed the salient property of the morphisms between monoids. And then a second peculiar example of categories that I gave is that of a set. Right, so we can view any set as a category by viewing the set itself as the set of objects. And for any and for any 2 objects in X, the home category is either a point if the elements are the same, and the empty set if the elements are different. This is called the discrete category associated to X. So as an example, if you have a category, if I have a set with only only three elements, and you get 3 objects and 1 identity morphism between all of them. And then I told you that, so we have these 2 examples of categories. We have the example of monoids and we have the example of sets. And the category is some sort of generalization of monoids and sets. And therefore, the notion of morphism between categories should also be some sort of joint generalization of the notion of morphisms between a monoid and the notion of morphism between a set. And this is exactly what we get. So a funct gives you, so a funct between 2 categories C and D give you a map between the set of objects. So this is how a category looks a bit like a map between sets. But then for any 2 objects, in a category, and here for consistency, I should have written this slightly differently. For consistency, I should have written it like this. Then for any 2 objects, we get a morphism between the corresponding a map of sets between the corresponding sets of morphisms, obeying a bunch of rules that look basically just like the rules that we had for morphisms between monoids. All right. And then finally, I gave you the definitions of a natural transformation between 2 functors. So give me a sec. I'd like to open the window because it's getting a bit warm in here. Oh, I appear to have dislodged my iPad. I'll have to fix that in a sec. So while I'm getting a handle on this technical issue, this would be a great time to ask questions if you want to.
Does anyone has a question? I know there is a bit of latency, so Adrian was just recapping what we went through since last time. Some of you were saying that it would be helpful to start a little bit from the basics, the beginning thing. But for those of you who are advanced, you can ask more advanced technical questions. Okay, so this is not just a newbies thing. The reason Adrian is going through the basic stuff is because some of them are already attending. I have asked him to do this, so you can ask questions at any level, advanced level. So if you are already a practitioner, using category theory. So we do have a question. Let me show it. Yeah, what is the relation between set and category theory?
Between sheaf theory and category theory.
Sheaf theory, yeah, sorry. Sheaf, yeah.
Well, let's get this sorted out quickly. All right, so So sheaf theory is just a thing which is difficult to formulate if you don't have category theory. That's basically what it. I mean, I don't want to go into sheaf theory right now because it would take us a little bit far afield. But a sheaf is a sort of pre-sheaf satisfying certain properties. And what is a pre-sheaf? A pre-sheaf is a type of functor, and a morphism between pre-sheaves is then a type of natural transformation. And it is possible to just write down all of these things without using category theory. It just becomes very tedious. But you can, and some people do. And for the very basics of sheaf theory, category theory is not super necessary. But as soon as you start wanting to do something, well, you know, the more you want to do with sheaves, the higher the pain tolerance you will need to have in order to get it done without using category theory. All right, so let me see if I can close the window again without disconnecting my iPad. So I'm being very gentle here.
Yeah, no worries. Yeah. And just to add to this thing, I think this is one of the reasons that Grothendieck definitely loved. I think he was probably, if not the person who invented sheaf theory.
No, so
someone else.
sheaves, yeah, so sheaves were invented, I think, by Leray.
Okay.
But I'm not.
Or he introduced them in the context of algebraic geometry, something like that.
And right, but Grothendieck became very interested in category theory because he noticed that so-called abelian sheaves form an abelian category, a notion which he defined, and he basically on his own launched the sort of second wave of homological algebra. So anyway, that was a quick history lesson. All right, so
thank you.
So let's continue with these basics, and then I can move on to some new stuff. So let me just give you some motivation that I sort of kind of crammed in at the very end of the last AMA to start off with to talk about natural transformations. So if you have x and y being topological spaces, so y is a topological space, x is a topological space, and y is a topological space, and you have two continuous maps between them. Right. Then there's a notion of homotopy between these two maps. And what is a homotopy? A homotopy is just a map from x cross 0, 1 to y, such that such that h restricted to x times 0 is equals to f, and h restricted to x cross 1 is equals to g. So it's some sort of interpolation between the functions f and the functions g and the function g. And somewhat similarly, you could actually define a natural transformation between f and g in this way. So let's try this and see what happens. So first, what do we replace the interval 0 to 1 with? So let me just add a date here so that we can keep track of when I've been talking about various things. There we go. So we replace 0, 1 with the following category. It has two objects. called 0 and 1. And it has one morphism, which I'll just call bracket 0, 1 bracket. And then we have, and then as in every category, so in the beginning I'll draw them, but at some point I'll stop. So like with every category, we have the identity of 0, and we have the identity at 1, and then of course the morphism 0, 1 precomposed with the identity at 0 is equals to 0, 1 is equals to the to 0, 1 post-composed with the identity at 1, as usual. And I don't know, I want to give this here a new name because I'll very soon be considering actual pairs of objects. So let's see. What shall I call this? I'll just call this iota. And then if I have categories, C and Y, and I have two functors, F and G, then I can again try to write down some sort of homotopy between, oh, so this guy here should have been pointing in the other direction. Some sort of homotopy going from F to D. So we'll just try to do exactly the same thing as we did before. Eta will just be a functor from 0, 1 times C Y. Right, so first I need to tell you what this here is. So whenever you have two categories, right, so whenever you have two categories, call them A and B so that we don't, oh, I've obviously already gotten myself confused. This should be C and D. Let's call our categories A and B. Then the object of A cross B are just pairs. So objects of A and the objects of B. And so let's say we have a morphism. So the morphisms from A cross B from A1 cross B1. Oh, rats. From the pair A1, B1 to A2, B2. Right, so this pair here and this pair here, they're both elements of this guy. So I've taken an object, A1 is an object of A, and B1 is an object of A, A2 is an object of A, B2 is an object of B. then this here is exactly what you think it is. It's just going to be all the morphisms from A1 to A2 times all the morphisms from A2 and to B2. So now let's think about, let's go back to our natural transformation and try to figure out what a morphism here looks like. Okay, so now so first of all, let's just assume that, let's say we have two objects, C1 and C2. In C, then whenever I start off, whenever I have a morphism like this from 0, C1, actually let's rename these C0 and C1 in order to make the indices line up nicely. So whenever I have a morphism from 0, C0, to 1 C0, then this gives me some morphism from eta 0 C0 to eta 1 C0. So this here is a morphism in D. But we want this to be some way of going from F to G. So we'll just force by we'll just force we'll just assume that this is our map from F C0 to G C0. And if we go back to the definition of a natural transformation that we had last time, we get exactly, we get the structure, namely for every object C0 and C, we get a morphism. We get a morphism like this. But then we also had some property, and how do we recover this property? Well, let's replace this here by some, oops, that's not the pen I wanted. Let's replace this here by something more interesting. Let's replace this here by 0 C0 to 1 C1. Then this morphism here, recall, is just a pair of morphisms, right? So this is the pair of morphisms iota. Oh, so I need to specify morphism C0 to C1. Let's call it F. This is the pair iota F. This one up here was iota identity on C0. Then I can split this morphism here up into something more interesting. I can split it up into the following. I have 0 C0, 1 C1, and up here I can do 1 C0, and down here I can do 0, C1. I will just tell you what the morphisms are. So this here is iota, identity, and C0. So this is exactly right. So this is exactly the same morphism we've already considered once. And here at the bottom, we do the same thing with C1. But here we do the identity on 0 times F. And here we do the pair identity on 1 and F. And as an exercise, you can check that. As an exercise, you should check that if you compose this guy with this guy, you get the same thing as a composition of this guy with this guy. And in this case, we say that this square commutes. And if I plug this in to iota, so if I write iota everywhere, sorry, not iota, eta everywhere, then by applying this convention up here, I then again get f of C0, f of C1, and I apply G G of C0, and up here I have eta of C0, and then here I plug in F, I get an F of C1, here with F, and here I get G of C1, and here I get G applied to F, and here I get eta of C1. So to summarize, a natural transformation between functors is just as in the case for continuous maps, is a functor from the product 0, 1, comma C across C to D, such that if I restrict eta to 0 across C, I get a functor F. If I restrict eta to 1 across C, I get G. So if you're familiar with homotopies in topological spaces, then the idea of a functor should feel very natural to you. So here I mostly just wanted to give some motivation why one might think of this notion of morphism between functors. All right, so are there any questions at this point? So let's see. All right, I don't see any questions. Let me continue then. Or is there anything in the comments? Oh, there's a bunch going on. There's a bunch of stuff going on in the comments. Yeah, okay, so Tony Haldroyd is asking about size issues in category theory, and basically, so there are two levels at which, or at least two levels in which size issues matter. One of these issues is is literally just the problem that you already have in set theory, just propagating to category theory. So what do I mean? Like if I want to define the category of sets, then I'm not literally allowed to talk about the collection of objects being the set of sets, because the set of sets already doesn't exist on a set theoretical level, as Tony correctly points out, due to set theoretical difficulties. And so one reason why you're not allowed to, why you have to be careful about these things in category theory is just for the same reason you have to be careful about these things just already in set theory. Then the second reason you might care about these things is because you want to limit the this is a bad sentence. You want to limit the size of indexing category in limits and co-limits. So you don't yet know what limits and co-limits are, but once you do, I can tell you how the issues show up there again. So George is asking, can a natural transformation be extended to an interpolation like topological homotopy? I don't know what George means by extended. Oh, we get more. Oh, I see. Yeah, I don't know what George means by extended, but I'll carry on for a bit, and maybe in the meantime, George can elaborate, and then I can get back to George's question. So where was I going with this? So let me recall quickly our running examples from this AMA. So that's these examples here. Let me just copy paste these. All right, so I want to discuss all of these examples quickly because they'll just come up over and over again. And let me just rearrange them in the order which we'll be discussing them. So I see. So is George asking the following? Is George asking, let's say I have two categories, C and D, and I have a functor F, and I have a functor G, and I have a functor H, and I have a natural transformation theta from F to G, and what letter comes after eta? Theta, and I have a letter theta from G to H. Is George asking whether I can get a natural transformation from F to H? So let's see if this is what is asked for. Well, let me just answer this question, and then we'll see whether this is what George wanted to know. The answer is yes. You can compose these two. You can compose these two natural transformations to get a new natural transformation, and you get them basically the way you would think. Right, the way you do it is you sorry, there was just a weird noise from the floor above, so I got distracted. Okay, so I'm running out of space here a bit. So all right, so the way that you do this is that right, so for every object, C and Z, we have a morphism from f of C to G of C to H of C. So this here is eta of C, and this here is theta of C. And then you just take the composition. So this gives you the structure part of the natural transformation, and then you can just check that everything commutes. And this just follows from the following, right? So if I then have a morphism from C0 to C1, so let's turn all of this here into C0, then I get, maybe we should give this guy a name, so I have F applied to F of C1, and then here I get G applied to F, G of C1, and here of eta C1, and here of theta C1, H of C1, and here of H of F, and then you can just verify that all of this commutes, right? So this composed with this guy is the same thing as, well, we already know that this composed with this is the same as this composed with this. So all of this composed together is the same as all of this composed together. And then I just do the same trick to see that all of this composed together is the same as all of this together. So we get that going this way around is the same thing as going this way around. So then we get a new natural transformation. And in fact, you can then show that for any two categories, C and D, you get a category of functors between C and D. So here the objects are functors and the morphisms are natural transformations. All right. So if there are no more questions, let's move on to the four running examples I want to talk about. So is it clear to everyone what the category of sets looks like? So here the objects are just sets and the morphisms are just maps of sets, and you can compose maps of sets to get new maps of sets. So let's look at the category of topological spaces. So the category of topological spaces. So the category of topological spaces. Let's give these guys names up here already. So we have the category of sets, category of topological spaces, category of groups, and the category of vector spaces. And I'll just always be working over the real numbers, but you could be working over any field, for example, the complex numbers. Right, so the objects in topological spaces are topological spaces. Not a very exciting thing to say. And then the morphisms in topological spaces are continuous maps. So I won't give the full definition of a topological space because that would take us too far afield. But a topological space is a pair x and tau x, where x is a set and tau x is a subset of the power set of x. This is the power set satisfying some conditions. And these here are called the open sets. Right, so as an example, if you take Rn with its standard topology, then a set U is open if and only if for all x in U there exists some epsilon greater than 0 such that for all y in Rn we have that the distance between x and y being smaller than epsilon implies that y is in U. Right. So what this means is that if this here is our subset U in Rn, and I don't know why the U disappeared. So we have a point U, our set U, and we have a point X. Then what this is basically telling you is that if you nudge eggs in any direction, as long as this direction is small enough, then you're still in U. So notably, the boundary of U is not part of U, it's only the interior. And this is why these sets are called open. The idea is that There are the sets where if you nudge just a little bit, you still remain in the set. And then a continuous map. So from now on, I will stop writing. From now on, I'll stop writing tau x. So I'll often just write x. Right. So a map between x and y, where x and y are topological spaces, is continuous so we'll just write it out a bit more cleanly. Then a continuous map is, well, yeah, I'm already regretting my decision to be a bit sloppy, but I'll keep on. So a continuous map is a map of sets which will again just denote x to y, such that for all v in tau y, so for every open set, we have that the inverse image is in tau x. So now let us verify that what we get is indeed a category. So let's go back to the very top. We need to verify that we have a bunch of structure. So this structure is the structure is a collection of objects. Well, we have that. That's the topological spaces. And then for every two objects, we need to verify that we have a set of objects. Well, I've just told you what those are. And then for every triple of objects, I need to give you the composition. And for every object, I need to give you the identity map. So what we want to do is we want to check. So let's check the identity map first. So the identity map from x to x is continuous, right? Because let's say that u is in tau x, then we have that the inverse image of u is just u, which is again in tau x. So that gave us the identity part of the definition. And now let's say that we have two continuous maps. So x to y, z, x, g. So let's say that they're both continuous. And let's say that W is an open map of Z. Sorry, an open subset of Z. Then we have that the preimage of W is equals to the preimage of W under F and G. But this here is by assumption an open subset of Y. And because the preimage of any open subset of Y is an open subset of X, this here altogether is an open subset of X. So we now have, we've also defined the composition. So this here is supposed to be a little circle. And now we have to verify all the properties. So we need to verify that any continuous map, pre and post composed with an identity map, this gives you back the same map, which I think is obvious. And then we also need to show that if I have a quadruple of objects, where are we? I also need to show that if we have a quadruple of objects, then the order of composition doesn't matter, and that the order of composition does not matter just follows from the fact that we're considering maps of sets with properties, right? So if you have two topological spaces, then a continuous map is a map between the underlying sets satisfying some property. But because we have this property, because we have this associativity condition already for maps of sets, we automatically inherit it for continuous maps between topological spaces. All right, so let's see. It's 9:04 where I am. So I'll just go through the remaining two examples of groups and vector spaces, and then I'll call it a day for today. So last time I told you what a monoid is, and because I told you what a monoid is, it's very easy to tell you what a group is. So definition, a group is a monoid. All right, so a monoid is a triple consisting of some set of elements together with some composition and some identity element satisfying, where did they go? Satisfying all of these axioms here. And a group is required to, actually, I can just copy this quickly so that you can see it. So this was the definition of a monoid. And so a group is a monoid such that for all elements V and G, there exists an element called the inverse of G. Right, so here the notation is referring to, so all of this, this is the complete notation. This is the name of the element in G, such that G times G inverse is the same as G inverse times G is equals to the identity. And then, by definition, and as above, this triple here is often denoted just by G. And then a group homomorphism homomorphism is a map, the group homomorphism from G to H is a map of sets which are getting called F from G to H, such that such that for all pairs G1, G2 in G, we have that F of G1 composed with G2, we get F of G1 composed with F of G2. And this is just the same definition as a as a monoid homomorphism, where we just view the groups of monoids. Right, so what I should maybe mention is that F taking E to E is automatic. So group homomorphism is just a monoid homomorphism if you use the groups as monoids. All right. And then again, you need to check that that group homomorphism is composed and that the identity morphism is a group homomorphism. So let's check that. So let's check this. The identity morphism from G to G is a group homomorphism. Right, so for all G1, G2, and G, we have that the identity applied to G1 times G2 is just by definition G1 times G2, which is again just by definition the identity applied to G1 composed with the identity applied to G2. And oh yes, and then if I have two group homomorphisms, so I'm going from G to H, from H to K, I have F and O. I see, now I'm going to run into problems if I call my second morphism G. So let me just go Greek again and call this guy here phi, and this guy here psi. And then I have that for all G1 and G2 and G, we want to check that phi composed with psi is a group homomorphism. And it's just the same old game. We just pass everything through. So now we have psi applied to G1, composed of phi applied to G2. And here we apply, so now we apply phi to the first factor, giving us phi composed with phi of G1. Then group composition, and now we apply psi to the second factor, so this gives us psi composed with phi of G2. So again, we see that the composition that group homomorphisms compose. And just as for topological spaces, you get the associativity conditions for triples of composable morphisms. You just inherit it from the same condition for sets, and also obviously that the identity homomorphism composed with any group homomorphism just gives you back the original group homomorphism. It is again a property which you inherit from sets. All right, so I will end here for today, and then in 2 weeks' time, I will tell you about properties of what you can do once you have fixed such a category, what you can do inside. And the three most important things that we'll talk about is I'll tell you about isomorphisms in categories. So one of the first things you can ask whenever you have a category of things is when are two of these things the same? And the notion of sameness in category theory is encoded by the notion of an isomorphism. And then I will show how the notions of monomorphisms and of injections and surjections generalize to categories. And then I'll also tell you about some universal properties. All right. So are there any final things you want me to clear up for today?
Yeah, I think you went through a good deal of going over some of the baseline stuff that I think it was very useful to everyone. So thank you for that.
Yeah, no worries.
And thank you for history correction as well about who invented sheaf.
Yeah, I think it was Leray. I mean, we can just
Yeah,
have
it
a
was.
quick
It
look
was.
at,
Yeah. It was not
was it here?
Grothendieck.
Okay.
Yeah, obviously I heard about it while the whole thing in the context of algebraic geometry when I was reading some stuff about Grothendieck. Yeah. Anyone has any questions before we let Adrian go? Again, as I said, these sessions have both advanced and basic components. So if you are a little bit more advanced or more advanced, you can also ask very advanced technical questions. But I guess it's too late now. Maybe you can save them for the next session. I want to thank Adrian for taking his time to do this, and we look forward to having him back again in 2 weeks. So I will end the stream. Thank you, everyone, also who showed up. This will be obviously it's been recorded, so I will circulate the recording to the others who could not join us today. So yeah, have a great rest of the week, everyone. I will just end the stream.